Let's continue with the solution for question number 15. We need to complete this reaction, and we also have to identify the reaction as SN1 or SN2. For you to know if the reaction will go through the SN1 mechanism or the SN2 mechanism, you need to identify what type of haloalkane you have. In this case, we have a primary haloalkane. This carbon is only attached to another carbon. So it's a primary haloalkane. Okay, let's identify the leaving group. The leaving group is this halogen. And what is the nucleophile in this case? But we have sodium cyanide, so we have this is an ionic compound. So this one is your nucleophile, and it's a good nucleophile. DMSO, what type of solvent is DMSO? DMSO is a polar aprotic solvent, and we know that they work the best in SN2 reaction. For SN2 reaction, we prefer good nucleophiles such as this one. So this reaction will go through the SN2 mechanism. Okay? So SN2 is a nucleophilic substitution reaction, meaning that you will replace the halogen with your nucleophile. So you will just draw what you have here, but instead of Br, you're just going to have the nucleophile. And that's it. Let's take a look at the next reaction. Okay, for C, first you need to identify what type of haloalkane you have, and in this case it's a secondary haloalkane, and in that case you could have the SN1 or the SN2. So it's not enough for you to know, okay, well, this is going to be the SN1. No, you have to keep looking. Let's take a look at what type of nucleophile you have. The nucleophile in this case is this one. This is a hydrogen. And you have acetone here. Acetone is a polar aprotic solvent. And this nucleophile is a good nucleophile. Good nucleophile with a polar aprotic solvent that is telling you that you will have the SN2 reaction mechanism. SN2, okay, but that is also telling you that the stereochemistry, when you have to consider the stereochemistry, when you are forming a chiral center for the reaction product, you had to know what type of reaction you have. And for SN2, what you have is the inversion of configuration, meaning that this will be your reaction product. And you will have the Br as your leaving group. Let's take a look at the next question. For this one, we have a secondary haloalkane. Well, in this case, it's a haloalkene. It has a double bond there. And if you form a carbocation in this case, it could go and now be more stable due to the resonance. So we could say, okay, if we do form a carbocation here, it could be stable due to this double bond. So it is possible to form a carbocation in this case. Let's take a look at the type of nucleophile that we have. We have acetic acid as a nucleophile, and this is a poor nucleophile. So we have a secondary haloalkene with a poor nucleophile that is telling you that you will have the SN1 reaction mechanism. And when we have SN1, we will have the racemic mixture. If your reaction product has a chiral center. So we will just draw just the same as you see, but instead of the Br, this is your leaving group, this halogen, you will have the nucleophile. But keep in mind, you will not put the hydrogen. And you will understand that when you go over the step-by-step reaction mechanism. And the other one, it will look like when you have the racemic mixture, instead of facing you, it's gonna be at the back. And you will have the Br, but because this hydrogen will now be just form HBr.